didn't know the time was up. I'm sure many of you have questions, and I apologize because we don't have time for questions. So let's get ready for our next speaker. Let me introduce Professor Sang-Hoon Lee. He was already introduced a little bit by our previous speaker. Professor Sang-Hoon Lee is an assistant professor of liberal arts at the 경남 National University of Science and Technology, it's GN Tech, and he received his PhD degrees in physics at KAIST. And today he will be talking to us about uncovering hidden mutual importance in networks via information entropy. So let's welcome Professor Lee.
Okay, first of all, thank you very much to the organizer for giving me this great opportunity to talk about my recent work about the uncovering hidden mutual importance in the networks via information entropy. There are lots of some buzzwords here, but I'm sure I'll make sure to introduce this concept to the more general audience than physics, which is my field. So, first of all, I'm working in 경남 National University of Science and Technology, located in Jinju, about 2.5 hour drive from here to the south. So it's not that quite far from here. And it's always a pleasure to return to Daejeon, which is kind of my academic hometown. I graduated KAIST, which is nearby here. And I have to thank all of my the precious collaborators, and especially Mi-jin, Eun, Byung-hee. They are the leading forces to work to all of these analysis. So I'm just introduce these ideas here. So I'm going to start my presentation with a little anecdote. When I was a high school student, I'm hiding the name of my high school because this is not a quite honorable story to the high school. There was a theft case in our dormitory, and a teacher said that you may think that you are just borrowing your friend's stuff without bothering to tell him. However, if you think he's your friend, but he doesn't think you are his friend, you are a thief. So, kind of very interesting way of saying blaming the thief. But it made me think that is it possible to have this kind of a concept? Directional friendship. And 20 years has passed, and now we know that there is a directional friendship actually, especially in online world. Of course, we know on Twitter, we have this following relationship. So for example, Professor Mi-young Cha and I follow each other, so we are kind of mutual friend. But I personally follow the journal, the scientific magazine Nature, and President Moon Jae-in, and CEO of Apple, Tim Cook. But there's no reason for them to follow me back, just an ordinary researcher. So there's certainly this kind of friendship, that directional friendship. I hope this doesn't mean that I'm a thief, but anyway. So you may think that this kind of a relationship is visible in online world. So there's a competitor of this particular SNS, which is this F service. And you may think that this is of course it's possible to have a followership relationship on Facebook as well. But usually these two social network services are distinguished by the directionality. That's the general perception of these two services, which is always the true. For example, you are supposed to like your boss's post on Facebook. So yes, I took this cartoon from Japan Times, which I believe has similar culture to us. But so in reality, the directionality is not always visible. So they are actually in terms of the nominal sense, they are friends, mutual friends in Facebook. But in reality, they are such a certain kind of a hierarchy that forces these poor salarymen to like his boss's post. So it's not always visible. So is there any way to distinguish this direction or extract this hidden directional relationship from this apparently mutual relationship? That is the first part of my research question. So maybe they are not very different to each other. So there can be many different ways to quantify this directional relationship, but I would like to focus on this part. So there can be some different degrees of mutual importance based on these different types of weight or the quantified the degree of quantified degree of the mutual interaction. So I took this example. The first one is this central node I, denoted by node I in this network, and the second part is this right-hand side, the node in this network. If you look at this, these two nodes both have 4 friends, denoted by the degree 4. And if you sum up these, the weight on these edges, they are all the same as the 32. But clearly they are different. Of course, everyone can figure out why is it different. So of course, it's something different, but what is it? Of course, they are different because their weight distribution is different. The left case is quite homogeneously distributed, while the right side is quite heterogeneously distributed. So to quantify this difference, we have to use some probabilistic notion. So first, we normalize this weight by dividing this with this strength, which is the sum of all the weight around this node. And then this, I denoted this as a tilde Wij, is some kind of a normalized weight, or so we use this notion of normalized weight. I actually, this basic idea is taken from the paper I published with Yongyal there as well, and about 9 years ago. And most important part of this thing is this is the first appearance of the hidden directional information from here. Because if we normalize this same weight with the node i's strength, we denote this by Wij tilde. Or if we normalize this with the j's strength, they're clearly different, because even if this Wij and Wji is symmetric, because this denominator is different, they are different to each other. So it actually quantifies how importance of these edges for each node. So based on this difference, we first try to quantify the notion of the hidden directional information. So we especially use the 2 types of data set. The first one is the World Trade Web between the nations, which from data taken from this particular website. So it covers like about 50 years of the data about the international trade. And of course, this data set is originally directed and weighted. So it's the trade between the South Korea and the United States, and their export and import side. And basically, because we are interested in extracting the hidden directional relationship, we first merge these 2 directions by assigning it as a trade volume. But I'm going to come back to this the directional information, original directional information again, if the time is allowed, of course, later. So we merge this export side and the import side as a trade volume as a weighted information. So can we discover some kind of the international trade's hidden directional relationship? That is our first data set. The second data set is a quite different one. Sorry for the Korean and Chinese character, but this data set is about the annals of the Joseon Dynasty, which is a historical document recording all the important events happening in this Joseon Dynasty, lasted like 500 years ago in this land, the Korean Peninsula. And this network is constructed by the node in these networks are people, and the weights are the number of sentences mentioning them together. So this is kind of the character network linked or weighted by how often they interact in this historical record. So the first part is of course we can just apply the basic Pearson correlation relationship, the Pearson correlation coefficient between the Wij tilde and the Wji tilde. And we can get this standard notion of the Pearson correlation, and we call this mutuality. And this is actually a bit the technical part, but because these two sides, Wij tilde and Wji tilde, is related by this strength or the degree variable, they may be related to this degree correlation or strength correlation, which is I don't have much time to explain all the details, but which is basically only the structural properties of this network structure. So if you look at the change of World Trade Web over time in terms of this mutuality change and the degree correlation and the strength correlation, we can get this kind of somehow fluctuating part. The biggest fluctuation happened somewhere between 1980s and 1990s, and there can be some reason because of course we know that in this era there was a collapse of communism and there was also some oil crisis. So this may be responsible for this big shift in this mutual relationship structure. But the important thing is that if you look at this, the big fluctuation only happens in this structural side. So of course they are somehow similarly acting, but the degree of fluctuation is much smaller for this mutuality value. So we assume, or our suggestion is that even if the network structure itself is quite reshaped during this oil crisis or the collapse of communism, these weights are redistributed to mitigate this too large shift in this world order in the World Trade Web. And if you look at this annals of Joseon Dynasty, we also have this kind of notion that the mutuality is a bit larger than the structural properties. But of course, we need some null model to actually say that these changes are actually meaningful or not. So that's why we come up with this comparison to the case of shuffled weight as a null model. And these two examples, World Trade Web and Annals of Joseon Dynasty, they are very different in this case. If we shuffle all the weight in the World Trade Web, actually the mutuality becomes larger than the actual data. It means that the World Trade Web is actually less mutual than the null model, which is kind of counterintuitive, but that actually means that there are some certain hierarchy between these nations. So they are not quite mutual to each other because there are lots of dependent cases. And in comparison, if you look at these black dots and red dots, they're quite similar to each other. So it's almost like an expected mutuality by chance. So these two systems are very different. So I don't have much time, so I only introduce this the second part of my talk about this procedure to extracting only the important edges from this weight distribution. I already introduced this concept of the normalized weight. The important part is that these normalized weights are directed or asymmetric because the Wij tilde and Wji tilde is different. And because this is a probability variable, if you sum all of these around the node, they are unity, of course. But we are interested in the characterizing the heterogeneity or homogeneity of this notion. So we took this concept of Shannon entropy from information theory or statistical physics. We get this quantity, which is basically measuring the homogeneity of the work weights around node I. And I don't have much time to explain all the different types of entropy, so I just skip this part. But the important thing is that there is the scaling properties of this. So if the weights around a particular node is quite uniform to each other, they scale like a log of k, the degree, number of neighbors. If there is some dominant weight singled out and dominate all of these other edges, so in this case, these two edges are too dominant, so these very thin edges are almost negligible. In this case, because of these properties of entropy, this entropy becomes zero or vanishes. So if we actually exponentiate this quantity further, then we may get this number. We call this effective degree, which is if all of the neighbors are important, they are recovered to the original degree, and only one of the neighbors is important, it becomes 1 because the exponential of 0 is 1. So basically the notion is if we actually apply this concept to this case, they discover that in this case, if we actually calculate it, the effective degree is almost 4, and in this case, effective degree is almost 2. So we take all of these neighbors because they are all important to the central node. But in this case, only two of the neighbors are important, so we take this example. And again, there is some hidden directional information appearing, because if we take this kind of procedure for all of the nodes, we have some reciprocal edges, but some unidirectional edges. So this is also kind of an emergence of hidden directionality from the original undirected weighted network. So we also apply this. We try to investigate the properties of this hidden directed subnetwork for the two data sets I mentioned. So we define this kind of relative edge density and the reciprocity. I don't have much time to explain details, so I just explain this with this, just a big conclusion. So in cases of a World Trade Web, more edges are selected as a meaningful connection than the shuffled weight case, which is a null model in this case. But the fraction of reciprocal edges is actually smaller than the shuffled weight case, which is actually consistent with my previous result. The mutuality becomes larger when we shuffle the weight. But for the annals of Joseon Dynasty, they're all the similar number of edges are selected as a meaningful connection, and fraction of reciprocal edges is also very similar. So it's kind of expected by the null model. So even if we shuffle all the weight, in terms of this mutuality or the hidden directional information, there is not much information to extract from this annals of Joseon Dynasty. In contrast, in case of the World Trade Web, there are a lot of much richer information that we can actually exploit from this procedure. So the final part is again, is it possible to rediscover this original directed version? Because if we kind of infer or guess what is the effective directional information. So important part is this. So if we want to validate our methodology, we have to compare these two cases. Does this procedure really have the predictive power to actually recover this relationship? And we discovered that there is some certain kind of correlation between these two. And if we actually normalize this, if you use the normalized from this original direction to the version, there is correlation gets bigger. But the main message is so I'll conclude my talk with some main messages here. So of course there is a hidden directionality or dependency about the existing in the real world, which is not always visible, as I demonstrated by the Facebook friends example. And we would like to extract such a hidden information based on some measures from the information entropy. And also we apply this to temporally changing very different types of data. But of course we would love to apply our methodology to much larger types of data to get more general conclusions and things like this. And as a time, I think I already got over time. So I have to thank my organizer, and also, of course, I have to thank you for your direct attention to me. Thank you very much.